All right, welcome back to class. Today we're going to study the famous Newton's method. So Newton's method is a way to solve equations, a nice way, an efficient way. So we all know about the quadratic equation, of course, and we know that that can be, easily solved with the quadratic formula. But how do we solve something like this, a seventh degree polynomial equation? Turns out there is no formula. It was proven a couple hundred years ago that there is no quadratic type formula for anything greater than, I believe, fourth degree roots. So when there's an x to the seventh, there's no way to write down a nice formula in general that will always work. However, we can still find a decimal approximation of these roots, and the method is called Newton's method, and it uses calculus and tangent lines. So the idea is that we have some graph, and we would like to know where the graph crosses the x-axis. This is what we're looking for, right? This is our root. So we learned in our linearization chapter that we can approximate the graph by a tangent line. So let's draw our tangent line. And notice that it gives us an answer, but the answer is not the exact answer that we're looking for. So let's say x1 is where we started with, and this is the point, x1, y1, which is x1, f of x1. So we calculated the tangent line at x1, and we follow the tangent line back towards the x-axis. Remember, we want to know where the original graph, y equals f of x, where it crosses the x-axis, because that would solve the equation f of x equals 0. So we follow the tangent line, and we can calculate this number. That's going to be called x2. We're just simply finding the x-intercept of the linearization. So we'll solve that in a moment. Now the idea is this. So if we blow up this box here, so let's redraw what's inside that, that box right here. So it'll look, basically it'll be the same picture again. Well, actually, if I blow it up, then let me not draw the x and y axes, right? So let me not draw the y axis. So blowing it up, it looks something like this. And if I blow it up enough, here would be x2. So here, say, is the point x2, f of x2. Okay, so now in this picture, I'm right here. So in the big picture, I'm right here. That's x2. So that would be x2, f of x2. And in this picture, I'm over here at x2, f of x2, and then I just do this again. I find the tangent line, and I call this point x3. Notice I'm getting closer and closer, hopefully, to r, which is the real answer, which could be irrational, and we're never going to get there exactly. It's unlikely that we would get there exactly, depending on, I guess, what our guess is, but unlikely we'll ever get there exactly. But we are going to get closer and closer to the true answer. Okay, so here's another picture of what's going on here. And if you look in the textbook in section 4.8, you'll see an even nicer picture that that shows what's going on. So all right, so here is x1. Here's x1. We follow down the tangent line to x2. We jump up to the graph, take another tangent line, hit it at x3, jump up to the graph, another one, x4, steadily getting very close to r. All right. Now notice, though, it is possible to miss completely. Like, see if this is x2 right here, you totally missed the graph. So you have to be sufficiently close in a very technical way for this to work. We're not going to be worrying about that in calculus class, but in a more advanced math class, you can come up with exact conditions as to when Newton's method would work. But it is actually pretty complicated. It's not super easy to solve that kind of problem. Okay, so let's move on to the formula. All right, so we're going to form a sequence x1, x2, x3 that usually converges to r. First guess x1 should be near r. That's really the only rule. Make your first guess as close as you can to an estimate of where you think the answer should be. The intermediate value theorem could be used to show whether your guess is sufficient, is close or not. Okay, so we start with the linearization of f of x at x equals 1. And to find x2, we set the linearization, which is the y value of the equation, to 0, and solve for the intersection of the line and the x-axis. Setting it equal to 0, solving for x, we call that x2. So x2 is x1 minus f of x1 over f prime of x1. So, of course, if x prime of x1 is 0, you chose a really bad point to start Newton's method at, and it will not work. So that's giving you a hint. You don't want this denominator to be too close to 0, or you could miss the graph. Okay, x3 would be the same exact thing, but now with x2 taking the place of x1. So x3 is x2 minus f of x2 over f prime of x2. And proceeding inductively, this is called an inductive or recursive equation, the n plus 1th number is equal to the nth number minus the function of the nth number divided by the derivative at the nth number. Okay, so let's use Newton's method to approximate the solution to x cubed minus 2x minus 5. Okay, so first we need a guess. So it doesn't matter what you start your guess at. Why don't we just start with the number 2 and see if we start converging to an answer that looks reasonable. And then when we get an answer, we can check, plug it into the equation, and see how close we are to 0. Okay, so f of x is equal to x cubed minus 2x minus 5. Remember, we always solve equations of the form f of x equals 0. So we're assuming that this is the form of what we want to solve, and it is. F of x equals 0. You may have to put it into this form if it's not already in that form. Okay, to use Newton's method, so let's let x1, how about 2? Just a guess. It doesn't really matter how you guess it in our class. Just start with any number. Okay. We need to compute f of x1 and f prime of x1. All right, so let's compute the derivative. So that's 3x squared minus 2. And let's find x2 by hand first. So x2 would be x1, which is 2, minus f of 2. So it's plugging in 2 into the original function. 2 cubed minus 2 times 2 minus 5, all divided by the derivative at 2. So 3 times 2 squared minus 2. All right, so let me show you how to do this on your calculator in an efficient way. So first, let's store 2. 2 store into x. All right, we have x stored. Now, let's plug in our formula here. X minus f of x over f prime of x. So let's compute x minus fraction. So f of x would be x cubed minus 2x minus 5 divided by f prime of x, which is 3x squared, 3x squared minus 2. Okay, so I plugged in Newton's method here, and I got 21 over 10, and as a decimal, hitting the float decimal, that would be 2.1. Okay, so calculating this out, you get x2 is equal to 2.1. So now doing one more by hand, so what you do is to get x3, we go back and you put this answer, the x2 answer, back into the formula. So x3 would be 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5, all divided by 3 times 2.1 squared minus 2. Okay, to do this on the calculator in a quicker way, just store the answer we just got as your new x, and now go back to the expression where we have Newton's method stored, but now x is going to be 2.1, so it'll redo the calculation, and we got 2.094568,121. So I'll just approximate it by 2.0946. Now you would find x4 by plugging this in. So let's do this on the calculator a little more quickly. So I'm going to store it into x, and then I'm going to go back to Newton's formula, and I got 2.09455. It's almost as I got the same answer. When the numbers stabilize, it means you're really close to the answer. See, the numbers aren't changing. Let's try it again. Store this as x. Go back to Newton's formula. 2.09455. So as you can see, I think we're about as close as we're going to get. All right, so you can check the answer on your calculator. Numerical solve. It actually has Newton's method programmed in for you, but you will have to show this kind of work on the test. So keep that in mind. Okay. So let's solve this equation, setting it equal to 0 on the calculator. So it will be x cubed minus 2x minus 5 and equals 0. Okay. It wants us to put in a guess. It has the last number we were doing. Let's go try our guess that we did before. We started with 2. And the answer is 2.094551482. And what it does is it plugs it in the left and the right side for you, and it gets 0 when it subtracts them. So that's a check that the answer is accurate. Now, third degree polynomials actually have 3 solutions. This will only give us the real solution, but just for your own knowledge, there are 2 possibly complex solutions. So turns out for third degree polynomial, there is a formula to find the exact answer, like the quadratic formula. It's quite complicated though, so nobody really learns it. So A is 1, B is, that's the x squared term, that will be a 0. The C is -2, and the D is -5. All right, solving it. And so it has the answer we found, 2.09455. This one is complex. It's has an imaginary part. So it looks like it's about -1.05 plus 1.14i, and the other one will be its complex conjugate. So it works, and it gives us an answer in a nice, simple way. Okay. All right, so let's try another example. Use Newton's method to approximate the sixth root of 2. Okay, so we need to find a nice function, f of x, where f of r would be 0, and that would be the root we're looking for, sixth root of 2. So can you come up with a function, a nice function, whose 0 is that answer, whose root is that number we're looking for? And the answer is x to the 6 minus 2. So how do we find f of x? Well, let x equal the sixth root of 2, raise both sides to the sixth power, move the minus 2 to the left, move the 2 to the left, and there's our function, x to the 6 minus 2 equals 0. It's in the right form, f of x equals 0, right? What we want is f of x equal to 0. So f of x equals 0, f of x is x to the 6 minus 2. All right, so why don't you pause the video for a couple minutes, come up with your own first guess, and see if you can get this to work out. All right, welcome back. So let's let x1, let's let it equal to 1. We know that's not that far off from the sixth root of 2. So that should be a pretty good guess. It doesn't matter though. Guess whatever you like. I would guess a positive number because you can't, without getting an imaginary answer, you don't want to take the square root, the sixth root of a negative number. So guess positive for sure. All right, so f of x is right here. F prime of x, 6x to the fifth power. So Newton's method will be x n plus 1 is equal to xn minus xn to the sixth power minus 2 over 6xn to the fifth power. Do not choose your guess to be 0. That would be very bad, because then you'd have a 0 on the bottom of the fraction. Okay, so let's find x2, which would be x1 minus x1 to the 6 minus 2 over 6x1 to the fifth power. And that would equal 1 minus 1 to the 6 minus 2 over 6 times 1 to the fifth power. All right, so let's switch to the calculator. Okay, so we're going to store 1 as x, and let's plug in the Newton's formula. So it'll be x minus fraction x raised to the 6 minus 2 over 6x raised to the fifth power. All right, I got 7, 6. So let's store that as x and do Newton's formula again. 1.12644. Let's try it again. Store it as x. Go back to Newton's formula. 1.22, so we were at 1.26, now we're at 1.22. Let's see if we can stabilize these numbers. Let's store it back in X. Go back to Newton's formula again. 1.22, it looks like we've stabilized to about 4 digits already. Okay, so that's the idea for Newton's method. And turns out the best place to do this is actually on the computer. So let me just show you super quickly how we could program what we just did on Python. So at some point, you all are going to be taking a programming course. It's a brand new course we designed, and you'll learn how to solve problems, using a Python programming language. So this is called collabresearchgoogle.com. It's a free website made by Google that allows you to program a virtual machine. It's actually very powerful. You can do a lot of things here. I'll send you a link if you want to play around with this. But I recommend you start learning Python, especially when you have some free time. Maybe you can get a little head start on that course you have to take. All right, so don't worry about if you don't understand a lot of these syntaxes. So let's let x equal 1. That was our guess. And let's let n equal 1 while n is less than 10. First we want to print out our guess. So print x. And then we want to calculate our new Newton's number. So x equals x minus parentheses x raised to the 6th power minus 2 divided by parentheses 6 times x raised to the 5th power. Order of operations ensures that the exponent will go first. Notice you need to use multiplication. We didn't need it in the calculator, but here you do. All right, and then it's going to keep on looping this. Let's let n equal n plus 1. So it'll keep looping this until n gets to 10. Let's give it a try. It's initializing. And as you can see, we got our numbers. If we want 20 numbers, yeah. So this is a little tiny program. It's called Python. And there are loads of free books online. I could help you get started if you're interested. There are videos, courses, tons and tons of resources if you actually want to do something serious with Python. All right, so let's go back to the whiteboard and look at one last problem, and then we'll be done. Okay, use Newton's method to solve cosine of x equals x. So in this case, f of x is not 0, but that's easily corrected by just moving it over to the other side. So we saw this on exam 1. See, if cosine of r equals r, then that's the same thing as saying cosine of r minus r is 0. So our missing function is cosine of x minus x, and that will solve the original equation. Okay, so let's start with a guess. Well, we're looking for a root of this equation. So f of x is cosine of x minus x. So if we try 0, cosine of 0 is 1. If we try pi, if we try pi, or if we try 2 pi, it's also, let's see if we can find a negative answer. Let's try, and we can use our calculator. Let's try f of pi. So f of pi would be cosine of pi minus pi. So that's -1 minus pi, which is definitely less than 0. So there is a root between 0 and pi by the intermediate value theorem. So why don't we just, pi is about 3.14. Why don't we just let our first guess be like 1.5? It doesn't matter. You could choose whatever number you like on our exams, but if you want to understand it a little more deeply, something like this is definitely helpful. All right, so let's program this into our calculator. So 1.5, we're going to store that as x. And let's write down the expression for Newton's formula. So x minus f of x over f prime of x. So that's x minus cosine of x minus x, all divided by the derivative, which is negative sine of x minus 1. So stay away from points where the sine is equal to -1, or you'll get a 0 on the bottom. Okay, so plugging this expression into our calculator. So x minus fraction cosine of x minus x and negative sine of x minus 1. All right, I got negative 0.7844. Let's store this as x. Do it again. 0.739. Try again. Looks like we're stabilizing 0.739. So that's the idea. You can go to check your answer to the numerical solving and solve cosine of x minus x equals 0. And that was our first guess. Let's go to 1.5 again. It's essentially doing Newton's method for you. And as you can see, we did zero in on the correct answer. All right, so I hope you enjoyed this lesson on Newton's method. And have a good weekend, everybody, and take care.